All right, guys, are you ready? So this is the first question. So the first question is, how many ways can a family of 5 wear 20 identical masks if, like moths to the light of science, they flutter to comply to Dr. Fauci's latest recommendation? So they have to wear at least 2 masks. Yes? So if they wear at least 2 masks, then the masks are identical, guys. So the situation is as follows. You can say this is the number of masks worn by person number 1, plus this is the number of masks worn by person number 2, all the way to x5, the number of masks worn by person number 5, and they will have to put all the 20 masks. They don't want any mask not to be on their face. So what's the situation is that each xk is bigger than or equal to 2. Yes? So then what I can do is I can simply subtract 2 from everywhere here. So I simply have x1 minus 2 plus x2 minus 2 all the way to x5 minus 2, and that would be 20 minus 10. So altogether then I have 10. You agree? So then we have the situation where we have the summation of y1 plus y2 plus y5 equal to 10, where in this case yk has to be bigger than or equal to 0. So how many possibilities are there to distribute 10 masks? 10 masks among those people now. So they already, yes. So 10 masks among those people, they're identical. So what you do is you can imagine, that's exactly Fnu. It's you can imagine that there are 4 partition bars. They're identical altogether. Then we have how many objects? We have 10 objects and 4 partition bars. So we have 14 total objects. And out of those objects, we just have to decide. So we have how many spaces? We have 14 spaces. Which of those spaces are occupied by partition bars? So it's like this. That's the answer. Okay. Everybody understands? Any questions on the first question? On the first problem? It's 14, choose 4. Or equally, you can say 14, choose 10, all the same. Right? So remember, if you can look into my notes, the supermarket analogy, right? So basically, what is the 14? 14 are my spaces, right? So I have this, what do you call it? This treadmill. This treadmill or whatever you call it. Conveyor belt, thank you, right? This conveyor belt, and on the conveyor belt, I place all the items and I place the bars, right? So by knowing by selecting the spaces containing the bars, I know exactly where, which items belong to which person. That's why the bars are used in a store. So that's the idea. Everybody understands? Yes? Here is a small question I want to ask you guys. Just out of curiosity. One time, I think yesterday on What When Where game, they asked this question, which I was surprised they asked. I wonder if you would right away know it. So they said, name a country name a country from the 19th century of which it was said the sun never sets there. What would you write? So that's the question that they had. Name a country from the 19th century where the sun never sets. Yes, so good, right? So that's why I was surprised they messaged it. It's just it seems so obvious, right? So they also answered. Yes, it's right away. The sun never sets over the British Empire. Everybody heard it, I think, or almost everybody. I just wanted to see. I couldn't understand why it made it to the show. Yeah, sorry. So back to this thing. Okay, you all understood question 1. No questions for question 1. Yes, I'm erasing it. All right. So now let's talk about this one. So how many ways to split 12 people into 4 teams of size 3? Notice that, guys. So if it's 4 teams of size 3, I'm not assigning them tasks. So the way I can think of it is I would break it. I write the Kafka protocol, and I have 1, 2. Right. So here are the 4 teams. So this is team 1, team 2, team 3, team 4. So the T1, T2, T3, T4 are my dragons. Yes. So that means that what I should have is 12. Choose 4, 4. Choose 3, 3, 3. All right. It should be 3, 3, 3, 3. Right. And the only problem is that there is no difference between if the same people are in team 1 are moved to team 2, there is no difference. So I would have to erase those teams, which means that I can rearrange in 4 factorial ways. So it's 1 over 4 factorial. So the answer is 12 factorial divided by 3 factorial to the power of 4 and 4 factorial. Any questions? Good, yes, understandable. Okay, let's move on. All right, this one, traveling circus. There are many ways of solving this particular question. There is one that is very simple. So let's see what we want. We have 20 cars. 2 cars are carrying clowns. 2 cars house trapeze artists. 4 are for lions. 4 for bears. 4 for elephants. So we want to see no elephant or bear preceding the car with lions. So it seems that I really care about the elephants and the lions and the bears. You agree? So altogether, I care about those 12 creatures, or 12 cars, right? 12 cars. Now I can use symmetry, guys. Do you agree that I can encode in my message? I can say which was the first among those types of cars that I've seen. So there are several ways to solve it. I'm going to show you right now the quickest, simplest in calculation. And we can figure out other ways to do that as well. So we should see if this happened. I mean, my Kafka protocol is which line? Which line did I see? And the possibilities are with the possibilities are 4 for lines. It's 1, 2, 3, or 4, which is the first line that I've seen, and then order of remaining cards. And even better, which line I've seen if it's success. I don't even need this. I can ignore the remaining. So which first line did I see if I was successful? And in general, divided by animal, which could be lion or bear or elephant. Yes. So the simplest way to answer this is it's 4 divided by 12. 4 are for lions, 4 over 12. So the answer is, the probability is 1 out of 3. You understand how I figured it out, guys? I reduced the sample space quite a lot. And I said, well, in this situation, I will see either line 1, line 2, line 3, line 4, or line 5 as my first, if I'm successful, right? And other creatures come in other sequence. Or the very first of the among those categories that I see is one of those 12 animals. Do you understand the symmetry that I did, guys? That's so I could have solved it. I can show you another way to solve it. But I decided to encode my sample space as mentioning the very first animal among the 12 that I will see, right? The very first. So the very first could be equally likely either a lion or any one of the lions or any one of the bears or any one of the elephants. Yes? But success means that the first I've seen was one of the lions. So there are 4 possibilities. And in general, out of 12. Is this clear what I did? Yes, I'm moving on. Yes, guys. Or you want to see other solutions? You should be able to, for the same problem, to construct at least 2 solutions or more. Right? So you can play around. This one is just the easiest one, computationally.
Would you show a different solution?
Yes, of course. So I'm erasing this. You remember the number is, I can make it more. I can include all the animals. I can include only the animals of interest. I can do so many things. I'm going to show another solution. Are you ready? So this you understood. I'm erasing it. Correct, guys? So I'm going to clear. And here is another solution. So I'm going to now consider the successes. Basically, I'm going to consider just the animals of interest altogether. So I'm going to say which was first, lion, and then rest. So that would be my my ordering of the numerator, and the denominator will simply, that means success. First was lion, and then one of the lions, and then the remaining lions together with the remaining animals were together. And here just the ordering of the just order of animals. Order of animals. So that would be 4. Now, once I selected the line, there are now 13 remaining animals. So it's 13 factorial. Sorry, there are 11, not 13, 11. Right, 4 possibilities for the first. Now, once I mentioned the first, they are going to be 11 other animals. So 11 factorial other animals with their respective order, divided by total order of the animals I can see is 12 factorial. Here is another solution. You can see clearly that I can just factor out 4 over 12, and the remaining thing is cancelled. So I get the same solution this way. It's a different approach. Here I arranged all the animals just among themselves. So here I decided to mention the full sequence of animals that I see. So you stay, oh, I see a lion, and then I see an elephant, then I see another lion, then I see a bear, then I see another bear, then I see a third bear, then I see an elephant, you see? So here I decided to mention all of them. In my previous example, I just look at it and I stare. I see my first animal, and then I stop looking. Because, okay, first animal could be which? But through universes could be any of the available 12. And it's what I want if it was a lion. So no elephant or bear precedes the first card with lion, which means the first card I see is the card of a lion. Right? Which are 4 possibilities, 4 universes in which the first card I see is a lion, and there are 12 possibilities for the first thing that I will see. Good? So, and you can make it more complicated, of course. You see, this calculation is not as nice. It's already involving more simplifications. The one I came up with before was better. Now let's look at question number 4. 18 fair dice are rolled simultaneously. What is the probability of getting each value 1 through 6 3 times? Okay, So you understood what happened here, guys? Yes, I need to get each value exactly 3 times. So for that, I just need to decide which of the die display which value, right? Which of the die will display which value. So the categories, the dragons here will be the values, right? So each value, so dragon 1 will swallow 3 die. Dragon 2 will swallow 3 dice, and so on and so forth, right? So that means that we should have 18 choose, well, basically 18, 3, 3, 3, 3, 3, 3. You agree? Yeah, so this is the distribution of the 18 dice into the grouping, and then of course that now I already know that now which die display which value, and that's supposed to be divided by each die can produce independently any one of the 6 values, so it's 6 to the power of 18. So the answer is 18 factorial divided by 3 factorial to the power of 6 and times 6 to the power of 18. That's the probability. Good? Questions? All right, then I'm going to move to 5. Let's see. A certain non-standard deck has 60 cards. There are 10 distinct denominations, with each denomination having 6 suits. So we just have a strange deck of cards, right? So it has 60 cards, and it has 10 distinct denominations. So you understand my idea of a card is that it has 2 numbers, 1 number in the front, 10 numbers in the front, and 6 numbers in the back. That's the suit. Understood? If 2 players randomly take 5 cards each, what is the probability that there is no overlap in the denominations between the players, and where one withdraws 2 pairs and another a triple? So that's the situation: 2 pairs and another is taking out a triple. So for that situation, I have to first of all see which of those people withdrew the pair and which the triple. So it's 2 possibilities: which is the pair, which is the triple, times, and let me know afterwards if you want to see the protocol. I mean, I have it in my head, times which particular denominations were picked as the pair, right? So which is picked as the pair, and that would be 10 choose 2. Do you agree? You see where 10 choose 2 comes, guys? Because 2 denominations for the pair. And then what are the suit values for those pairs? So first has, and then the suit values for the pair is 6 choose 2. So that's the suit values. Now next I can say, what about the remaining card? The remaining card is, well, 10 choose 2, so we have 8. Now 8 choose 1 times 6 for its suit. And I'm done with person number 1. I mean, that's the selection for person 1. For person 3, you see that we have we cannot have overlap of numbers, so D is not equal to any of the previous ones. So we have 7 choose 1 for the triple. We have yes, 7 choose 1 for the triple, times 6 choose 3 for the denominations on the for the suits on the triple. I'm sorry. So 6 choose 3 times what remains. Now we have 6 choose 2 for the remaining cards, and the denominations for each of them is 6 and 6, so it's 6 squared. So this is my numerator, and my denominator will be in general, the first player can basically, I can select any of the cards and distribute them to players. So my denominator can be simply something like 60 choose 5 for the first player, and 55 choose 5 for the second player. Should the 6 choose 2 be squared? This one, right? So why should it be squared? We take two denominations, two suits for the two cards. It's the y squared. You mean here the second 6 choose 2? Why I picked the color for this guy and for that guy.
No, just like you squared the 6 in the 3 pair because you
let's go over that one more time to be sure. So you see the protocol is here. I would mention the 2 here is because I either mentioned player 1 or player 2 as the guy that is getting the pair, right? So that's why it's times 2. The possibility is player 1, player 2. So here's the 2. Next is the pair. We have 10 denominations. 10 choose 2 is the front value of the pair. For them, 6 choose 2. You are right. Yes, I think because 6 choose 2 is the denominations for first pair, and then for the second one it should be squared. Thank you. Right? You see why? Because 6 choose 2. Those are 2 values that go for first pair, and then 2 values that go to the next pair. Also 6 choose 2. Right? So 6 choose 2 for A and 6 choose 2 for B. So that's correct. It should be squared. Thank you for noticing. And then what remains is that I removed now 2 cards from my denominations. I'm only having 8 denominations left. From that denomination, I must pick 1 to create C. And then I must give it a suit. So that's why I multiplied by 6, right? So 2 numbers here specify the full card. If you look at this, that's actually one way to verify is that for each card, there must be 2 values, 2 numbers, right? Well, I'm not sure if know what you did. What do you mean by finding BB? So what do you mean by finding the probability? You have to be careful. I can see what you did. You can calculate if this is correct or not. You see the idea. Yes, guys. I mean, this is the situation. So I have 7 choose 1 because I now have only 7 available denominations, 1 for all the D's. And then 6 choose 3 is how to assign them suits. And then I have E and F, and E and F means I have now only 6 cards left. I choose 2 of them, and then I assign, so I have here 6 choose 2 for the values of E and F, and then I assign one a 6 and the other one 6 possibilities. So is this. Any questions? Can you do 48 choose? Yes, you can, of course. It's the same. It doesn't matter, right? I decided to continue to specify the cards by first mentioning the front number and then the suit. But I could have just eliminated the previous cards and said, well, among the remaining ones, just pick 1 card. You just have to be careful. The 2 in the start is because it's either player 1 or player 2. So the way I think of it, guys, I just didn't write it, but I think of Kafka protocol. I think what is my document? So I have a success protocol. So one person got 2 pairs, the other person got a triple, and they don't overlap. So in my success protocol, I say, okay, first box, I write which player got the pair. And then I write the particular pair combination. And then I write the particular triple combination. Make sense? So this is just the numerator is just describing how I carry the protocol. Understand? Good. Now this one, let's see what we have here. So question number 6. So there are 150 rooms in the castle, and the ghost of Banco goes to only one of the rooms, right? So and Macbeth sleeps randomly in one of the 150 rooms, and the question is, what's the probability that he does not encounter the ghost of Banco, right? So it just basically means that each time it's the probability of encountering the ghost of Banco is the probability of not encountering for each day independently is 1 minus 1 over 150. Do you agree? That's the probability of not encountering that ghost. Yes, and you can do that either using third chapter, or you can do it even from this information. So it's 1 minus 1 over 50 to which days? For 150 nights. So that means fail to encounter 150 nights, but we have this number, and so this number is what? It is simply, you tell me what is the number? So this is what number? Approximately. Which is not by calculator, but very specifically the approximation is what? E to the power of -1. Very good. So that's the good approximation for it, see? It's like e to the -1. Clear? You should just recognize that 1 minus 1 over a large number to that power of the large number, it's essentially e to the -1. Okay. Now we are doing 7. Coin comes up heads with a known probability P. In order to ensure fair outcomes, it is suggested to toss the coin twice. If the outcome is double H or double tail, ignore the toss and just do it again. If the outcome is tail head, interpret the outcome as heads. If the outcome is head tail, interpret as tails. Show that this corrective procedure makes the coin fair. It's almost intuitive that it will, guys, because it matches success and failure against each other. You understand? So I have failure success or success failure, and because each toss is independent of the previous one, they should balance. Do you agree? So it's an obvious way to to simulate a fair coin if you have a biased one. So the way you can show that this works is something like in our class we can calculate the probability of head. Probability that I interpret it as head means that I either get heads on the first trial or heads on second trial, heads on third trial, and each time, of course, I consider tossing the coin twice. You understand? I toss the coin twice, and then if the result is ignorable, I repeat. So what is that equal to? Probability of heads equal to the infinite sum of the number of tosses I had to perform. So I had to perform, let's say, 1 toss all the way to infinitely many tosses of what? So that if I had to perform k tosses, what do you mean? I have to either get heads, or so basically, if I get something homogeneous each trial, I ignore the result. HH or TT, I ignore the trial, right? And if I get HT, then I know it's tails. If I get TH, then it's heads. Okay, so the result is what? So I toss it how many numbers? So probability. So it's just they're broken in two. So here is two values, here is two values, and so on. Yes. So what am I going to do? So if it's this, I consider 1, 2, 3, and then on the KF I have to have success. KF trial is tail and then heads. You agree? And before it's neither tail heads or tail tail, right? So how many? What's the probability that it's neither tail tail? Sorry, that is not neither head tail or tail head. They're exactly 1/2 possibility. So this is 1/2. This is 1/2. This is 1/2. Whereas this one is not 1/2. Sorry, I don't know the probability. So this would be. My apologies. Right. So this would be what the probability that I don't get. So it's 1 minus p squared minus 1 minus p squared. You agree? Because p squared means I got head. 1 minus p squared I got. Apologies, 1 second. I mean this. Not 1 minus. I mean this means that I either got head or tail, right? Agreed? So it's p squared plus 1 minus p squared. Yes, good. So we have this. And the last outcome is p1 minus p. So the result is simply p squared plus 1 minus p squared times p times 1 minus p. Good. And then what's the sum? And this is to the power of k minus 1. So what is the result? The result is simply, once I sum this geometric series, it's going to be p 1 minus p divided by 1 minus p squared minus 1 minus p squared. That's what I should be getting, right? So what do we get? We can simplify it by, from here, I'm going to factor out, from the denominator, I'll factor out 1 minus p. So it is, the denominator is 1 minus p, and here I have 1 plus p minus 1 plus p. Let's factor, I just factor out 1 minus p out from the denominator. Here I have p, 1 minus p. What happens is this crosses out, and so I am left with p divided by 2p, which is 1/2, just as I expected. Yes? You with me, guys? Yes, I mean, it was, I mean, you don't even need to do the calculation to know that that should work. Why? Because you see what we do. The coin is not fair, but each toss is independent of another. So if I match failure against success or success against failure, then of course they're equally likely, right? Success, failure, or failure, success, same thing, because each toss is independent, right? So if I'm forcing the game to either end in success, failure, or failure, success, then each of them is going to have the same likelihood. So I knew the answer would be 1/2 without this calculation. No, you don't have to have the same calculation as me. Why not? I mean, you might. We'll see what you wrote. You see, guys, right? Maybe you argued by intuition, and I'll see what happened here. This is kind of just to prove, to drum a point in, but you see, tosses are independent. right? So, and I'm forcing the game to end in success, failure, or failure, success. So because they're independent, success, failure, and failure, success is the same, like the same outcome, same probability outcome. So they have to be equally likely. Make sense? It's like I can commute the letter. Success, failure, failure, success, I can commute it. All right, I'm clearing this. Now we go to problem number 8. 10 balls are randomly and sequentially drawn from a ball containing 20 balls numbered 1 through 20. If the drawing is done with replacement, compute the probability of obtaining a monotone, non-decreasing sequence. You understand? I take the balls and then I put them back. And I do that until I have gathered, I said, 10 balls, right? So think about it, guys. So I have to have a monotone sequence. There are several ways of solving this, right? So let's think. So first of all, guys, if I obtain a monotone sequence, here is one way to solve it. Yes, I obtain a monotone sequence, then look at it. In this case, I obtain some number of 1, some number of 2, some number of 4, some number of 5, some number of 6, right? You agree? I obtain the same number several times, perhaps. Maybe 0 times, maybe sometimes. So I can say that we can look at the equation x1 plus x2 all the way plus x20 equal to 10, right? So this means how many balls I gathered of type 1. This is how many times I gathered balls of type 2. Like in this example, type 1 was, look at it here, type 1 is 1, type 2 is 3, type 5 is, I don't know how many, at least 2. Make sense? Now, if the sequence is monotone, then of course I know how to arrange this result, right? Because I know where they came. If I pull them out monotonically, I know where they came from. And of course, some of them can be 0. So here xk can be equal or bigger than 0. Because I might have never gathered ball number 20, so it could be equal to 0. So the number of monotonic non-decreasing sequences is equivalent to the number of solutions to this equation. You agree? Each solution to this equation is just what is x1, what is x2, what is x3. It tells me how to arrange it to be a success. So that means that that what I should have is, since I have 20 here and 10 balls, so that I should have, and each of them is bigger than 0, I should have 19 divisions. So it's 10 plus 19 divisions. Choose 10, where they're located, right? You agree where the items are located? So this is my numerator, and my denominator is if I gathered 10 balls out of 20, each of them can be any of the 20. So it's 20 to the power of 10. So my probability is 29 choose 10 divided by 20 choose 10. I can come up with another procedure if you want. Do you want to see another procedure? I solved it 2 ways. Well, 29 choose 10 is what I did, no, right? So you did it in the same. 29 choose 9, you mean? Why choose 9? All right, so here are the items, and then I have to partition into 20. I have to partition 10 items into 20 parts, so I have to have 19 partitions. What's the other way? So you understood this one, yes? Right? So I'm going to erase it. So I came up with this way, and I came up, I think, with another way. Let me see if I can recall it. So the other way is I'm going to say, well, it's a monotone sequence, right? So I need to know how many times is the sequence jumping, actually strictly increasing, right? So how many times does the sequence increase? So you can say, let's say the sequence can increase up to 10 times. So we can say something like summation in the numerator, where k equal to 0 all the way to k equal to, so 0 means non-increasing, and then I can have increase after each term. First term, then increase, then increase, then increase. So all the way to 9 terms, I believe, right? K0 to 9 maximum increases, right? So you start with a number, and then the next is bigger, the next is bigger, the next is bigger. That's how many actual increases by moving up we can have. Agreed? So it's K0 to 9, and then if I have those increases, where did they happen? Those increases could have happened anywhere in the 9 position. So not the first, but could happen in the second, third, fourth, all the way to 10. So anywhere in the 9 position. So it would be 9 choose k. 9 choose k times, and then times the particular numbers that are available. So then if I had k increases, then I had to take 20 choose k plus 1 numbers. Right? K increases, there are k plus 1 numbers that I had to pick. Once I know those numbers, I place them in order and I know where they jump. So it's this, and divided by, again, 20 to the power of 10. That's another way to do this that I thought of. It has summation, so it looks a little less pleasant. You can see that what you have here, it's 9 choose k. You can see identity, guys. So k0 to 9, right? K0 to 9, and then we basically have like 2 categories. We have 9 out of 9 items, how many were chosen, out of 20 items, how many chosen. So this you can recognize still by identity, guys, because this is just a subset. It's like boys and girls, right? We have 9 boys and 20 girls, and this is how many individuals we have to pick, right? We have to pick how do you say that? Yes. So let me think. Yeah. So in the numerator, I can write it this way, I think. K0 to 9. 9 choose k, and here we have 20 choose 20 choose 19 minus k. I can write it this way, divided by 20 to the power of 10. Yes, because you see, guys, 20 choose k is the same as 20 choose 20 minus k plus 1, which is 19 minus k. Well, James, sorry I lost you. He's already gone. All right, you're seeing this guy, guys? So, and then look at it, guys. K plus 19 minus k means that I'm choosing 19 individuals to go on a trip with me, 9 boys and 20 girls altogether. So that means that here I'm considering all the possibilities. I'm just taking a group of 19, and I'm considering all the possibilities. How many of those 19 are going to be boys? How many of them are going to be girls? Yes. So then you can see that this is again the same thing as 29 choose 19 divided by 20 to the power of 10, and you can also write it as 29 choose 10, 20 to the 10. So that's another way, and because I was able to show that they're equal, that's an evidence that both my procedures are correct. Do you see that? You understand the idea, guys? Yes. I mean, so I thought this is the first way I thought to do it, and then the one I presented before, it was just faster. So, but I thought of it later. So you understand? I thought if the sequence is increasing, I can just mention which numbers were picked based on the number of times the actual increase happened. 0 means that the same number repeats. So 0 means I need to pick one number. If I have 2 increases, I have to pick 3 numbers. Right? 2 increases means 3 numbers, and then I right away know the distribution. Right? So I need to specify the place where the increase happens and the numbers. And once I know the place in the sequence, in the placements of 10 where the increase happened, I know everything. Good? Any questions, guys? I'm hoping I'm explaining well enough. My head is a bit empty, so I feel strange. Yes? Explanation goes through? All right, we're now doing 9. Ten cards are randomly chosen from a deck of 52 and sorted into 4 piles by suit type. Okay, so we take 10 cards and we sort by suit type. What is the probability that the largest pile has 4 cards? The next largest has 3, the next has 2, and the smallest has 1 card. Make sense? So 10 cards and by suit type. So then, the largest. So first of all, which is largest? There are 4 suits. Which is the next largest, and so on. There are 4 factorial possibilities. So you can see it's 4 factorial possibilities to assign the order of suits. And then we have 4 cards, and then 3 and whatnot. So then it's what? It's simply 4 factorial. Then we have 13 choose 3 for the first type. Even we can do that. Yeah, so 13 choose 3. 13 choose 4, my apologies. So 13 choose 4 cards that went to 1 suit. Then we have so that means 13 choose 4 went to, let's say, 1 suit. Then we have 1 second. So then for the other suit, we have another available 13 cards. So then we have 13 choose 3, and then another card. We have another pile. We have 13 available. Choose 2, and 13 choose 1. Okay, so that's going to solve it, and that's divided by 52 choose 10. One second before I finish to be sure. 52 choose 10. So the numerator describes which suit received what, and that's automatically true once I know which cards I picked. So 52 choose 10. If I list those cards, I automatically know how to sort them into suits. So that's right. Good. Questions about it, guys?
No questions.
So this is understandable how I did it, yes?
Yeah.
You agree with me? You had the same answer?
Yes.
All right. So there are 100 practice problems, and the students know the answer to precisely one. So they know that one of the answers is e to the power of -1. You understand? So out of 100 questions, exactly one question has answer e to the -1. If none of the 30 students have bothered thinking about these problems and randomly answer one of the questions as e to the -1, what is the probability that no one picks the right question? Do you understand? Basically, e to the -1 is the answer to exactly one of the 100 questions. 40 students, each of them independently answers the question. All the 100 ones, and just randomly assigns e to the -1 to one of those questions. So that should be what? That should be simply that they fail to pick the right one is 1 minus 1 over 100. You agree? To the power of 40. Right? That means that every single one of them failed to pick the right question. So, I mean, this is, I said approximate solution. No, so I mean, I said approximate solution because I want you to see what it is. I mean, it's almost like the previous question. It's very similar. Do you agree? So here is how you can approximate it. Look at it. What do you want it to be? You want it, of course, to be 1 minus 1 over 100 to the power of 100. Do you agree? You want it to be the power of 100. So, but you don't. So what do? You just say it's to the power of 100 and then to the power of 40 over 100. Yes? So what is it approximately? This is approximately e to the power of -1 to the power of 40 over 100, which is simply e to the power of minus 0.4. You agree? So it's approximately, well, I mean, how did you calculate it, Fnu? Did you place it in a calculator? I mean, I'm not grading a calculator, right? I mean, I'm interested whether or not you can process it. I mean, it's not easy to take such power, right? So let's see. Give me a second. All right, so, but that's not interesting, guys. Come on. Let's see, a second, let's see. Yeah, that's not interesting what you do, guys. You should have told me e to the power of minus 0.4, and that would show that you know something. Right? I mean, it's like I asked you to write an essay in French, and you just use Google Translate. So, right, what have you learned from that? Well, that's an approximation. That's what I meant. We'll see how much I deduct for it. Relax. Why are you so worried about the exam? I mean, the point is you should all see this type of thing. You should just avoid you should just see the idea. All right. All right. This one. 11. Do you understand a story argument for that, guys? A story argument for this situation or combinatorial proof for this identity? Anyone bother doing it? All right, so why is that the case? So what you can have is you can see where are the what elements do I select? So so I can say we have the people. We can draw a picture. Let's say here is person person 1, person 2 is shorter, person 3 is shorter, and all the way to person n, who is the shortest of them all. Okay, that's maybe just the story I'm coming right now up with, right? So then I have to take k of those individuals with me. So if so what could have happened? Either maybe I did not pick the shortest guy. I did not pick the shortest guy with me. So I have altogether n-1 people available. And out of them, I picked my team. Or what did I do? Or I picked the shortest guy and did not pick the guy that's slightly taller. Do you understand? You see how I'm going with it, guys? I go based on the guy that I did not pick. First, I did not pick the first guy, the nth guy. I'm sorry, I didn't pick the shortest guy. That's n-1 choose k. Then I say, well, let's suppose I did pick the shortest guy, but did not pick the next short. And so altogether, I have n-2 available candidates, and out of them, I have to still pick k-1. Or I picked both shortest guy and the next short guy, and I did not pick the third shortest guy. So that would be n-3, choose k-2, and so on. You understand the idea? Yes, I know it would work, and that would count everybody because I think of it this way. Let's say, let me suppose I have just 5. So here I did not. First, I do not pick this one, right? And I so first I do not pick this one. So then I pick someone from here. Next, I do pick this one, and I don't pick this one. You see, so one line is impossible. So there must be disjoint. Do you see that? They are disjoint because the second row it contains a contradiction, because here is the contradiction, right? Here I did not pick the shortest guy. Here I did pick the shortest guy. So whatever I count here is disjoint from whatever I'll count here. Yes. Next, I would go like this. So I pick this guy, but did not pick this guy. You understand? So this is I would have told the story maybe this way: shortest guy, tallest guy, whatnot, and I could have drawn those circles. That's the way I would have answered. Good. All right, so find the necessary and sufficient condition on n and k that makes n choose k bigger than n choose k plus 1. So you can, for instance, do something like n choose k divided by n choose k plus 1. And what is that? This is n factorial over k factorial n minus k factorial divided by n factorial k plus 1 factorial n minus k minus 1 factorial. And when you simplify this thing, you get k plus 1 divided by n minus k, which is bigger than 1. You agree? So I just move things around in this fraction and I get this situation. So then I get that k plus 1 is bigger than n minus k. And that means that 2k is bigger than n minus 1, which means that k is bigger than n minus 1 over 2, for instance. You might be able to do that combinatorially if my brain is just, quitting on me. I'm a bit tired. Good? And the final question is the most interesting. Everybody understood this, guys? So it was not a very hard exam, I'm assuming, right? Or was it very hard? Just give me a sense of how enjoyably difficult was the exam. Okay, fine. Because yeah, I always imagine you're bored by those questions and I need to give you something more interesting. No, right? Good enough? No, enjoyable enough? You don't need a bit more thrills, right? Yes, good. Now the last question is from what, when, where, and I figured it out when I heard it. I cannot find where it was, but did anybody figure it out? You did, huh? So tell me, how was it done?
You take a line per page.
Yes, a line a page, precisely, right? So the way this book is done, guys, is that you take, the pages are not covering the book, they're like slices like this. All right? So there are, so I think a sonnet has altogether 14 lines. Right, exactly. Altogether has 14 lines, and we have 10 pages. You see, so basically here you have, so to speak. You see, so so of course, what you mean by pages, of course, that's the contention here, is that you have 10 copies of first line, 10 copies of second line, 10 copies of the next line, and you can just simultaneously for line 1 you can be on page 1, and for line 2 you can be simultaneously on page 7. You see? Yes, but so you have to be careful how, you see, you have to describe how, because the book is printed, you understand? You can just read the book and you have 10 to the power of something like that. So you had 10 to the power of 14. So 10 possibilities for here. So it's 10 times 10 times 10. So it's 10 to the power of 14 sonnets. Because you can take, you see basically what is meant by 10 pages here is that they are sliced, the pages are sliced, and you are able to make the first line any one of 10, and the second line any one of 10. Isn't it interesting? Did you figure it out, guys? So I figured this one out because I mean I had to, it's combinatorial, right? So I had to figure it out. So I was happy. Good. We finished this exam, huh? What do you say? Now all I have to do is grade it. I honestly am feeling like I'm just to tell you, okay, well, here's 100, just leave me alone so I don't have to read it. Well, before the semester is over. I don't know, when is our last class? Maybe you like me so much it will never be over. Yes, all right, so I'm gonna stop this recording, guys, and no, I do not even know what is stat 312.